Hello everyone, welcome to another video from the tutorial series Aspen Plus Mastery and Certification. My name is Tabish. In the last video, we have learned how to define power law and LHHW type of reaction kinetics in Aspen Plus. In this video, we will learn how to simulate batch reactor and electrolyzer model for the production of hydrogen from water electrolysis using Aspen Plus version 14. Before hands-on practice, let's first have a brief background about the batch reactor. Then we will solve a model example and move towards electrolyzer model. Since Aspen Plus is a steady-state simulator, it is conceptually a difficult task to understand how a batch reactor would work in a steady-state simulator. To better understand this concept, let's have a look on this flow diagram. This is the actual model that is programmed in the Aspen Plus and displayed as a single block in the reactor's palette. This flow diagram is taken from the reference textbook Learn Aspen Plus in 24 hours. I strongly encourage to read this textbook to better understand the operation and simulation of various blocks available in Aspen Plus. The actual model programmed in Aspen Plus is composed of 3 subunits, including a feed tank, a powder tank, and the batch reactor. The feed tank and powder tank are connected to the steady-state streams connected with the other steady-state units and provide the necessary buffer time to complete the batch processing. To further understand the operation of a batch reactor, let's consider following 3 terms. The first one is the batch time. This is a time required to transfer the feed material from tank 1 to the reactor. Then there is a batch processing time. That is the actual time required to convert the reactants into the products. And then there is a downtime. That is the time required to discharge the products from the batch reactor to the powder tank. And the sum of these 3 time requirements makes a complete cycle. One cycle can be considered equivalent to the residence time or the holding time in the steady-state reactors. So how the size or the volume of each unit changes with respect to time during a batch operation? Let's follow the volume profiles in this diagram. At the start of the cycle, tank 1 is completely filled with the feed, and during the batch feed time, the volume decreases and the material is transferred to the batch reactor until the required mass of the batch reactor has been transferred from the tank 1 to the reactor. During this phase, tank 1 volume drops, whereas the reactor volume increases to a value that remains more or less constant during the batch processing until the reactants have been converted into the products. While reactants are being converted into the products, a continuous steady-state feed stream recharges the depleted volume of tank 1. And during this phase, to ensure a steady-state conditions at the outlet of the batch reactor, tank 2 volume drops to fulfill the steady-state conditions of the product stream. In the downtime, when the reaction is completed, the material from the batch reactor is transferred to the tank 2, so the volume of the batch reactor drops to empty, whereas the volume of the powder tank 2 increases from minimum to a maximum level of the tank. And this process keeps going until the desired number of cycles are completed for the given simulation problem. So what kind of specifications are desired and what kind of problems this batch reactor can solve? Let's consider following table. The operational philosophy of the batch reactor in Aspen Plus includes batch simulation as well as semi-batch simulation. The reactor can be operated isothermally, or a well-defined temperature profile can be defined with respect to time. Alternatively, reactor can be simulated as an adiabatic reactor, or a well-defined heat duty profile with respect to time can be allocated to the reactor, or an external thermal fluid as a utility stream can be defined. The reactor can handle single phase including liquid or gas, or 2-phase or 3-phase system. One of the important specifications in simulating the batch reactor is stopping criteria. This criteria identifies when the solver should stop simulating the batch process. And the possible options as a stopping criteria includes batch processing time. Alternatively, conversion of a specified components or its composition can be defined as a stopping criteria. Otherwise, reactor volume or the size of the reactor in terms of mass or moles can be defined, or the temperature, pressure or vapor fraction reactor can be defined as a stopping criteria. The most common stopping criteria include either the processing time or the conversion of the reactants into the products. Depending upon the nature of the problem, remaining stopping criteria can also be defined. It is also possible to define multiple stopping criteria for the same problem. So whichever the criteria is met first, follow that criteria to stop the simulation. Let's consider following problem statement for practice of batch reactor. This is the same problem statement as simulated in the previous lecture, lecture 2.5. We'll solve the same example for the batch reactor and compare the results with the results of continuous stir tank reactor. The problem is ethyl acetate is produced from the reaction between ethanol and acetic acid, where the water is produced as a byproduct. The reaction kinetics in terms of power law, considering a reverse rate of reaction, are provided, and is also informed that the reaction takes place at 50 degrees Celsius and 101 kilopascal pressure. 100 kilomoles equimolar mixture of ethanol and acetic acid initially at 20 degrees Celsius is fed to the batch reactor and allowed to react for 3.18 minutes. So you are asked to calculate heat duty and reaction conversion and compare the batch reactor and CSTR reactor results when the CSTR results are discussed in detail in lecture 2.5. Let's open Aspen Plus and solve this exercise. Let's start a new simulation without any default template. Define the components for the simulation including ethanol, ethyl acetate. Let's put the search criteria equals to ethyl acetate and find now. Add to the components, search acetic acid, add to the components, and last component is water. Also add to the selected components. Rename the component ID for better specification. Acetate named as E acetate, acetic acid to A acid. Click next to enter the next input form. Choose method as NRTL HOC. Click next, next, and run the properties environment. Save the simulation before entering the simulation environment. Let's move to the simulation environment. First define the reaction. Add a new reaction from the reaction type general. Add new reaction. Name the reaction as, let's say, R1. Reactants are ethanol and acetic acid to produce ethyl acid and water. Since this reaction is reversible, that is observed from the rate equation provided, so check the box reaction is reversible. Coefficients for the reaction are -1 for the reactants and 1 for the products. So stoichiometry is defined. Let's enter the kinetics. Slightly let's reduce the window to open Word document in parallel. So the rate constant K is 1.206 into 10 to the power 6. Activation energy is 54,240 kilojoules per mole. Rate basis volume, reacting phase liquid, concentration, molarity, all these are fine, as well as reaction rate units in kilomoles per cubic meter per second. This is also fine. Exponent for the reactants is 1 and for the products for the forward rate is 0. On the equilibrium tab, define the compute equilibrium from built-in expression. Choose the concentrations to molarity. The coefficient A was calculated as 1.504 in the previous lecture, and that is equal to the natural log of equilibrium constant 4.5. Reaction is defined. Let's define the flow sheet. Let's choose RCSTR. Since in this case we will be using batch reactor as well, so let's use a feed stream duplicator to avoid the need of specifying feed stream separately for the batch reactor. Connect the feed stream, feed to the CSTR, rename as RCSTR to the block, product from the CSTR as PCSTR, feed as FCSTR, feed over here, and this is a duplicator block. So flow sheet is complete and required inputs incomplete. Let's proceed to enter the necessary requirements. Temperature of the feed stream is 20 degrees Celsius and entering at 101 kilopascal pressure at a rate of 100 kilomoles per hour, where methanol and acetic acid are present in the equimolar concentration. Enter the CSTR. Just like the example solved in lecture 2.5, put the pressure as 101 kilopascal. Reaction temperature is 50 degrees Celsius. The hold up phase is liquid. Define residence time instead of reactor volume since it is provided as 3.18 minute residence time. And on the kinetics tab, enter the reaction to the selected window. So the required inputs are complete. Save the file and run the simulation. Results for the CSTR are available. Let's have a look on the results. So the volume required is 314 liter. Residence time in hours is 0.053 hours. Have a look on the steam results. On the mole flow tab, out of 50 kilomoles per hour of ethanol and acetic acid, 23.5 kilomoles per hour remain unconverted, whereas 26.45 moles per hour are converted into the products. Let's solve the batch reactor and compare the results of the two. Choose a batch reactor model from the reactors palette and connect to the duplicator block. Rename the product stream as RBatch. This is feed to the RBatch and this is RBatch. Let's proceed to the input form of batch reactor and expand the window for the better view. As also discussed in the introduction section, the temperature specifications for the batch reactor can be given as a fixed constant temperature, or a temperature profile along the time can be defined, or a fixed duty can be defined. This specification can also be used to define the adiabatic operation of the batch reactor. Alternatively, time dependent heat duty can be defined, or a constant thermal fluid temperature can be defined. Let's choose a constant temperature of 50 degrees Celsius. On the same page, pressure specifications can be given as a fixed pressure or a reactor pressure profile. Let's continue with the default values. On the kinetics tab, shift the available reaction set to the selected reaction set. The two other important specifications are stop criteria and operation time. Let's first define the stop criteria. Here you can define single or multiple stop criteria. So whichever criteria is met first, the solver will stop the simulation. Let's define the first criteria as the reaction time. Location should be reactor and the variable is the time. So this is a reaction time. Other than reaction time, you can define the composition of a selected component in terms of moles or mass, conversion of a specific component, or total moles inside the reactor, or total mass accumulated inside the reactor, or the total volume of the reactor. Besides, you can define the reactor temperature, reactor pressure. This is typically relevant if the reaction is in the gas phase, or you can define a vapor fraction or vent related properties. Let's choose reaction time, and the reaction time by default should be given in the units of hours. So the reaction is 0.053 hours. That makes 3.18 minutes. Same time, let's define other specifications for the reaction conversion. Define the reaction conversion inside the reactor. Since this is a reversible reaction, so let's imagine a reaction conversion of 0.7. For conversion, you also need to specify the limiting reactant. Let's imagine ethanol in this case. Also, whether the conversion criteria should approach from the below or from the above. Since the conversion starts from 0 to a maximum value, it should approach from the below. Otherwise, for the reactant concentration, the criteria should approach from the above since initially the concentration is maximum. So depending upon the initial value, you can select the approach from below or approach from above. Stop criteria is defined. Let's define the operation time. In the operation time window, you can define a batch cycle as well as you need to define the temperature dependent results profile. Temperature dependent result profile is only for the display purposes, but the batch cycle defines the production rate or the consumption rate. Let's initiate with the same batch cycle time as of reaction time 3.18 minute. Let's define maximum calculation time of 10 minutes with the difference of half minute. So it should display 22 values for the reaction calculation. Let's even reduce it to 0.2 minutes so that we have a better resolution of the results. So all required inputs are complete. Let's save the file and run the simulation. So simulation is complete and results are available. Let's have a look on the results. In the results section, you can view the operating time, that is in fact the reaction time. Heat load per cycle is calculated and the heat duty per cycle is calculated. On the profiles tab, you can view the dynamic response of the reactor for pressure, temperature, cumulative duty, instantaneous duty, total mass. Total mass is the accumulated mass inside the reactor and totally depends on the batch feed time. Higher the batch feed time, more will be the feed introduced inside the batch reactor for conversion into the products. Let's have a look on the composition tab. On the composition tab, you can see different composition profiles including reactor molar composition, liquid and vapor molar compositions if two-phase mixture is involved, or the reactor accumulated mass. Let's have a look on the molar composition. Change the time to minutes and we can plot this composition profile. For plotting, go to this custom option, select the time on x-axis as minutes and the compositions on the y-axis. So this is how the concentration or the composition changes over the time. You can notice at the very start, the products have the minimum composition, whereas the reactants have the maximum composition that is equal to the feed composition. Over the period of time, the reactant concentration drops, whereas the product composition increases until to nearly an equilibrium values. Let's have a look on the other results. For the reactor accumulated mass, you can notice the mass of individual component that is available inside the reactor at any time during the processing time. On the reaction kinetics tab, you can notice the net reaction rate, magnitude of kinetic factors and the driving force at different times, and the reactor volume. You can notice that the reactor volume required for processing of the reaction mixture is almost the same as that of the CSTR. On the component generation rates tab, the rate of generations of all the components is given. On the stream results, you can notice temperature, pressure and phase of each stream. Let's have a look on the mole flows. These are the continuous inlet and outlet flows of all the components in the batch reactor. Though it is not intuitive to compare the flow rates in case of batch reactor and CSTR, but still for the sake of comparison, let's show the results of the CSTR product stream. As you can see, in case of CSTR, 23.54 moles of ethanol were leaving in the product stream, whereas in case of batch reactor, 17.007 kilomoles per hour of the same ethanol were leaving. That clearly indicates that higher number of moles of ethanol were converted in case of batch reactor compared to CSTR. Let's calculate how much is the conversion in both of these cases based on the continuous flow rates. For that purpose, let's make a room for the Excel sheet. So the conversion in case of batch reactor is equal to number of moles of ethanol entering the reactor minus number of moles of ethanol leaving the reactor divided by number of moles entering the reactor. So the fractional conversion is 0.66. Similarly, in case of CSTR, the fractional conversion is equal to number of moles entering the reactor minus number of moles leaving the reactor divided by number of moles entering the reactor. That is almost 0.53. Clearly, it indicates that almost 13% conversion is higher in case of batch reactor compared to CSTR case, though all the operational parameters were kept the same in both of these cases. And from operational parameters, I mean operating temperature, operating pressure and the residence time. So residence time in case of CSTR was 3.18 minutes. The similar time in case of batch reactor was the processing time or the reaction time that was used as a stopping criteria. This is a very classical case of conversion comparison between CSTR and the batch reactors. In case of CSTR, when fresh feed enters the reactor, it immediately mixes with the reaction mixture, therefore suddenly drops the concentration of the reactants. Whereas in case of batch reactor, the reactant concentration drops gradually over the period of time. So higher concentration of the reactant means higher reaction rate, and higher reaction rate means higher conversion. So the higher concentration in case of batch reactor leads to 66% conversion in comparison to 53% conversion in case of CSTR. I have already discussed how a batch reactor is simulated in a steady state simulator, but still these numbers for the batch reactor can be misleading, especially when calculating or comparing the fractional conversion with the CSTR. So the actual conversion of the batch reactor at any given case should depend on the actual number of moles or the composition present inside the reactor rather than the flow rates as displayed in the stream summary. So for that purpose, go to the profile, and in the composition tab, these are the actual molar concentrations of all the components, indicating change in the concentration over the period of time. So it is better to calculate the actual conversion from these concentration numbers rather than relying on the molar flow rates given in the stream summary table. Now let's consider how different parameters affect the performance of the batch reactor. For the purpose, let's go to the setup window in the stop criteria and operating time. Let's consider how reaction time affects the reactor performance. Before that, let's display relevant results in the new windows. Open the profiles tab as well as stream summary results. Let's change the reaction time to half of its original value. Run the simulation. Check the results. You can notice that still the total mass is the same inside the reactor. That is intuitive because changing reaction time does not change the accumulated mass inside the reactor, whereas it should affect the conversion. As you can clearly notice that reducing the reaction time clearly reduces the reaction conversion. Now the reaction conversion is 57.94%. So almost 8% conversion reduces by decreasing the reaction time to its half value. We can check the concentrations of individual components. The original concentration was 0.5 and now it's 0.21. That's the same number as displayed in terms of kilomoles per hour. Now let's see how the batch time or the cycle time affects the reaction conversion. Before that, change reaction time to its original value. Go to the operation times window and double the cycle time. The cycle time in fact includes the batch feed time, downtime, and the reaction time. Let's see whether increasing the cycle time while keeping the reaction time same does affect the accumulated mass inside the reactor or the conversion. Let's run the simulation. See the results in the profile. As you can clearly notice that the total accumulated mass inside the reactor has increased to almost its twice. To process this much amount of the reaction mixture, the reactor needs almost 628 liters volume, that is almost twice of its previous value. In the stream summary results, still you can notice that continuous flow rate is still the same, as well as reaction conversion is also the same. This clearly means that increasing the cycle time does not alter the reaction conversion. So Aspen strictly follows the reaction time as provided in the stopping criteria, and increasing in the cycle time directly increases the batch feed time. Let's play with the batch feed time. Keep the batch feed time originally the same as 3.18 minutes and run the simulation. Look for the results. The total mass accumulated inside the reactor is still the same, and the conversion is the same. So batch feed time with no downtime is exactly the same as that of total cycle time. What if we consider 1 minute as the downtime? So that means for every cycle, it will take 3.18 minutes to charge the reactor, then process the reaction mixture for again 3.18 minutes, and then takes 1 minute to discharge or unload the product. How adding downtime affects the reactor performance? Let's run the simulation. See the results in the profile. Still the total mass is the same. For composition, it's the same. For stream summary results, the continuous flow corresponding to the batch reactor has also been changed. So now the continuous flow rate is 76 kilomoles per hour instead of 100 kilomoles per hour. The inlet flow rate is 5306 kilograms per hour, but the outlet flow rate from the batch reactor is 4036 0.68 kilograms per hour. Apparently, it seems that the simulation does not respect the mass conservation. So that's why when dealing with the batch reactor, you should be very much clear about the results you are viewing. The results presented in the steam summary are averaged production rates from the batch reactor. The actual conversions, accumulated mass, or the concentrations of the individual components at any given time should be noticed from the batch reactor profile results. You can also notice that the generation rates are also given in kilomoles per hour. These are the same units as provided in the steam summary results. However, conceptually they are different. The numbers presented in this table indicates net generation rates of the components inside the reaction vessel, whereas in the steam summary results, the kilomoles per hour indicates the continuous flow rates of the components in the streams. So let's learn how to simulate electrolyzer block in Aspen Plus. The electrolyzer block serves the purpose of water electrolysis for the production of hydrogen and oxygen. There are two variants of electrolyzer block in Aspen Plus. One is the electrolyzer stack that can be modeled as a shortcut block as well as a rigorous block including the geometrical details of individual cell and the stack. The other variant is the electrolyzer module, that is a shortcut module, however includes the separation and purification of the product gases from water. The operational philosophy of the electrolyzer block includes the adiabatic operation as well as isothermal operation. The block can be simulated as a module, a shortcut stack or a rigorous stack. Having the information of input power or the current can determine the water consumption or the makeup water required. Otherwise, dictating the amount of water to be electrolyzed can determine the power requirement, and this option is only available in the module. The details of the specifications that can be provided in the rigorous model specifically includes number of stacks and number of cells in the each stack, specifications of the fluid channel, geometrical details of the membrane electrode assembly, as well as the mass transfer and electrical parameter specifications. Let's consider following case study to learn how to simulate electrolyzer block. Consider a stack that is fed with an alkaline water at 7 bar and 72 degrees Celsius at a rate of 445 kilograms per second. The composition of the feed is 25% potassium hydroxide solution. This feed is split into anode and cathode flows with the specifications that 75% of the feed by mass enters the anode channel, whereas remaining 25% leaves the splitter to enter the cathode channel. Itself, the stack block consists of 8 number of stacks, where each stack contains 230 cells. Total power consumption for the electrolysis is 20 megawatt. Since this is an industrial scale electrolyzer, so that's why the power consumption is so massive. Subsequently, the production rates of hydrogen and oxygen will be higher as well. Consider isothermal operation of the stack at 75 degrees Celsius means that any heat produced as a result of electrochemical reactions will be dissipated from the stack. The higher heating value efficiency of the stack is 80%. That indicates the conversion of chemical energy of the feed into the electrical energy. Also, the voltage efficiency is 80%. That indicates the actual voltage into the theoretical voltage, and the pressure drop on the both of the electrodes is 0.2 bar. Having these specifications, you are asked to perform shortcut simulation of the electrolyzer to determine the rate of production of hydrogen and oxygen. Hydrogen is produced at the cathode, whereas oxygen is produced at the anode. Also, you are asked to determine the rate of water consumption or the rate of makeup water. Then you are asked to perform the rigorous simulation using geometrical parameters as given below. Here are the geometrical parameters including the dimensions of electrodes, membrane, the fuel channel, the gas channel and the feed channel. For rigorous simulation, you are asked to determine the electrolyzer efficiency based on geometrical and electrical parameters. Also determine the energy requirements per unit mass of hydrogen production. Besides, you are also asked to perform the same simulation using electrolyzer module to determine the makeup water flow rate. And for this case, consider that the products leaving the electrodes are 96% pure. Let's open Aspen Plus and simulate this problem. For this problem, you can either start with the electrolyte template or you can start a new simulation without any default template. Let's start with the new simulation without selection of any default template. Add the components, and the components include water, hydrogen, oxygen, potassium hydroxide as an electrolyte. Since potassium hydroxide is a base, and during the electrolytic reactions, the solution chemistry will be involved instead of the apparent components. So let's use electrolyte wizard to define the solution chemistry. Proceed to next. Move QH to the selected components. We are not interested in any of the salt formation reaction. So let's add water dissociation reaction. Proceed next. I have experienced that the electrolyte NRTL model for this electrolysis simulation is preferred over the electrolyte NRTL with arc equation of state. The arc equation of state with the electrolyte NRTL is not appropriate to determine the vapor-liquid equilibrium or the vapor phase fraction. So let's proceed with the electrolyte NRTL method. Also here you need to make a selection between true component approach and the apparent component approach. For true component approach, all the constituents including molecules and ions will participate in the electrochemical reactions, whereas in the apparent component approach only the molecules will be considered for the simulation, though the solution chemistry will work during the simulation as well. For stack simulation in the shortcut case, it doesn't matter whether you prefer true component approach or the apparent component approach. However, the rigorous simulation specifically requires the apparent component approach. So let's proceed with the apparent component approach and finish the electrolyzer wizard. Let's have a look on the Henry's components. Henry's components for this case are hydrogen and oxygen, whereas water and potassium hydroxide are liquid phase components. Let's have a look on the method tabs. In the parameters section, in the binding interaction parameters, everything is defined now, and for the electrolyte energy pair parameters, they are also defined. All specifications have been provided, so click run to run the properties environment. Results are available. Let's save this file before entering the simulation environment. Let's move to the simulation environment. First, draw the flow sheet, for which we need a splitter and the electrolyzer block from the reactor palette. Connect all the streams. Now rename all the blocks and the streams. So once the flow sheet is defined, let's proceed to the next input form. Define the feed that enters the stack at 72 degrees Celsius and 7 bar pressure at a flow rate of 445 kilograms per second. The composition of the feed is by mass 75% water and 25% potassium hydroxide. Let's enter the next input form. For the splitter, it is defined that 75% of the feed enters the anode channel and the remaining 25% will enter the cathode channel. Proceed next. This is the input form of the electrolyzer. In the electrolyzer block, you can define the scope of simulation as stack only or module. Module includes separators in the model, whereas stack does not include the separators. So in case of stack, any unconverted water or potassium hydroxide will leave as the product stream in the anode and cathode outlet, whereas in case of module, since separators are programmed within the block, so you can define the purity of the output products. In case of stack, you can use shortcut as well as rigorous approaches, whereas in case of module, there is only one approach, and that is the shortcut approach. So let's practice the shortcut stack only. Enter the specifications. Let's minimize the model palette to make some room. Power input is 20 megawatt. There are 8 number of stacks and each stack contains 230 individual cells. Reaction temperature is 75 degrees Celsius. Otherwise you can define the duty. Anode and cathode pressure drops are 0.2 bar. So minus sign indicates the pressure drop over here. With this, all input specifications are complete except the efficiency. Default efficiency values are 1, whereas in the problem specifications high heating value efficiency was 0.8 as well as the voltage efficiency was also 0.8. Over here you can define high heating value efficiency or low heating value efficiency or voltage efficiency. If you are provided with the Faradaic efficiency, then you can define that efficiency over here. So required inputs are complete. Let's save the file and run the simulation. So results are available. Let's have a look on the results. For stack, you can view electrolyzer assembly results or stack results or cell results, or you can display all of the results in a single table. Here you can notice that the hydrogen production rate is 408.30 kilograms per hour. Similarly, the oxygen production rate and water consumption rates are also provided on mass basis as well as on mole basis. On mole basis, in total there is a consumption of 202.54 kilomoles per hour. That also indicates the requirement of the makeup water for a continuous operation of the electrolyzer. Since stoichiometrically, consumption of 1 mole of water corresponds to the production of 1 mole of hydrogen and half mole of oxygen. So the production rates of hydrogen and oxygen in the moles are also given here. Besides, we have defined 20 megawatt power consumption. So equivalently, the current will be 47.2 kilo amperes and the total stack voltage will be 423.69 volts. The input specifications for the efficiency are also reproduced here. Hydrogen purity and oxygen purity in the cathode channel and the anode channel respectively are also provided. Similarly, the vapor fraction on both of the channels is also provided. The duty of the electrolysis stack is also calculated, and that is 467.56 kilowatt. So that means for the isothermal operation of the stack at 75 degrees Celsius, there is 467.56 kilowatt thermal duty attached to the electrolyzer. With the 0.2 bar pressure drop, the discharge pressures in each of the fluid channels are 6.8 bar. The energy consumptions per unit mole of hydrogen production and per unit mass of hydrogen production is also calculated. So the specific energy of hydrogen production is 355 kilojoules per mole of hydrogen produced. That indicates the level of electrical energy required to produce the hydrogen. Similarly, the water consumption per unit mole and per unit mass for hydrogen production is also given. Besides, total power requirements, stack current, stack voltage and stack power are also provided. For each number of stacks, there was 20 megawatt power consumption. So per stack, there is 2.5 megawatt power consumption. Since all stacks are connected in parallel, the voltage will remain the same as 423.69 volts. Current is, however, distributed among 8 stacks. For each stack, there are 230 individual cells connected in series. So the voltage per cell will be 1.84 volts. Current will remain the same. So the total power consumption per cell is 10.86 kilowatt. Besides, you can view the stream results as well, indicating temperature, pressure and vapor fraction, liquid fraction of each of the stream. You can check the composition of the product streams. Since we have used apparent component approach, so potassium hydroxyl and hydronium ions are not provided in this case. Rather, the composition of KOH is presented. Here it is the purity of hydrogen in the cathode and purity of oxygen in the anode product stream. You can check the mass in the product streams as well as the volume of inlet and the product streams. So this is how you can simulate a shortcut electrolyzer block. Let's see how to define rigorous stack. For rigorous stack, you need to define the geometry of the cells as well. Let's first make some room to display the Word document and the Aspen file side by side. So here are the geometrical details of the electrodes and the membrane. The active area is 4 square meter. The channel length and width are 2 meter each. So define 4 square meter as the active area of anode and cathode. 2 meter width of both of the channels. 2 meter as length of the both channels. These are the specifications of the electrode. In a separate tab, we will define the specifications of the membrane. So the separation between electrode and separator is 1.25 millimeter. So let's define 1.25 millimeter. 1.25 millimeter for the cathode side. Thickness of the channel is 2 centimeter and the thickness of electrode is 2 mm. So let's define the thickness as 2 cm. Thickness of the channel is taken as thickness of the fluid channel in the direction of membrane electrode assembly, whereas the width and height of the channel are on the other two dimensions. Similarly, the thickness of electrode is 2 mm for anode as well as for the cathode. Bubble zone width is 0.5 mm. So all the required information for the electrode is complete. Let's enter the information for the membrane. For membrane, the active area is 4 square meter and the thickness of the membrane is 500 microns or half a millimeter. So let's enter 4 square meter and half millimeter thickness of the membrane. With this, all required information is complete and we are ready to run the simulation. Let's save the file first and run the simulation. Besides provided geometrical details, you can vary the activation free energy. You can also define the structural specifications including porosity and the tortuosity as well as the pore size. On the membranes tab, you can define the mass transfer coefficients of oxygen and hydrogen through membrane as well as wetness factor and the structural properties of the membrane. On the electrical tab, you can define the most important parameter as the reference exchange current density, besides the resistivity and charge transfer coefficient. By default, the charge transfer coefficient is 1.65 on the anode side and 0.73 on the cathode side. Provided that you have different values of the charge transfer coefficients for the Butler-Volmer equation, you can change these specifications. Similarly, the current density at equilibrium, defined as reference exchange current density, is given for the anode and cathode as a base specifications. So having the right numbers, you can change these specifications as well. Beside these details, you can define the Brugman exponent, osmotic drag coefficient as well as the rate constant of the recombination reaction. Let's have a look on the results. Again, for this case, the rate of hydrogen production, oxygen production and water consumption on mass basis as well as on mole basis are provided. Compared to the shortcut case, there is a slight difference in the water consumption and hydrogen and oxygen production rates. For the rigorous simulation, you can notice the current, voltage and the power. For this case, the higher heating value efficiency is 0.83 with the defined geometrical specifications. Similarly, the voltage efficiency is 0.82 and the Faradaic efficiency is almost 1. For the shortcut case, the voltage efficiency and higher heating value efficiency were close to 0.8. So there is only a slight difference between the two cases. You can also notice the purity of the product streams, duty of the electrolyzer, anode pressure and the cathode pressure. Since in this case, we have not defined how the pressure will be determined in the product streams. By default, in the rigorous model, the fixed pressure drop is 0. You can define the fixed values or you can determine using the correlations including the liquid head in pressure drop calculations. So let's rerun the calculations to determine the pressure drop in the fluid channels. So now the pressure drop is around 0.24 and 0.23 bars in the anode and cathode respectively. Also, the energy consumptions and water consumptions per unit moles and per unit mass of hydrogen are also provided. Besides, you can notice the electrical numbers that were not available in case of shortcut simulation. Here the reversible voltage is given. The reversible voltage at the provided conditions of feed composition, temperature and pressure is 1.18 volt, whereas actually the cell is operating at, you can check the cell voltage. The actual cell operating voltage is 1.78 volt. Besides, you can notice the overpotential values, the activation overpotential, ohmic overpotential and the concentration overpotential values are also provided. The overpotentials refer to the voltage loss because of the different associated resistances. For instance, the activation overpotential refers to the voltage loss due to kinetic resistance, ohmic refers to the ohmic resistance, and concentration over potential refers to the voltage loss due to mass transfer resistance. Current density on the anode and the cathode sides are also provided, that is 0.15 ampere per square centimeter. You can notice this number in terms of ampere per square meter, that is 1520 amperes per square meter. The exchange current densities on the anode and cathode sides are also calculated. In the input specifications, we have provided the reference exchange current density. So using free energy on the anode and cathode side, the exchange current densities have been calculated. The porosity on the anode and cathode sides, total resistance in the individual electrode and the electrolyte have also been calculated. The solution conductivity is also provided. On the transport tab, hydrogen and oxygen crossover through the membranes are also provided. Binary diffusion coefficients, Knudsen diffusion coefficients, as well as effective diffusion coefficients on both of the electrodes have been calculated. Let's have a look on the stream results. You can notice temperature, pressure and vapor fraction on all the streams. Similarly, the composition in the product stream is also calculated. So notice that in case of stack simulation, the products leaving from the electrolyzer block are not only gases produced as a result of water electrolysis, rather unconverted water as well as potassium hydroxide are also leaving along with the product streams. For practical purpose, they have to be separated from the product gases and recycled back to the inlet stream. And the depletion in the water concentration due to conversion into hydrogen and oxygen should be provided as a makeup water stream. This is how you can define the input specifications of the electrolyzer block and view different computer results. Let's have a look how to simulate a complete module that takes into account the flash separators to separate the product gases from the unconverted water. For that case, change the scope from stack only to module. In case of module, you don't need to specify anode and cathode streams individually. Rather you only provide a makeup water stream through the central connection port and provide the specifications within the module how that makeup water will enter the anode channel as well as in the cathode channel. So the flow split, the stack and the flash columns at the product streams, all three units are included within a single module. Besides modifying the connections, let's keep it stack only and separately simulate the electrolyzer module. For that case, define a separate electrolyzer. To avoid again defining the feed stream, let's use the duplicator block. Change the connection of the feed from the splitter to the duplicator. Take one stream from the duplicator to enter the rigorous stack and take second stream to enter at the central port. Also connect the product streams. Let's reconnect the inlet stream. Rename all the streams and the blocks. Let's proceed to the module to define the input specifications. Change the scope to module. Enter the specifications. Provide the specifications as were available in the previous case as 20 megawatt power, total 8 number of stacks, 230 cells in each stack, operating temperature as 75 degrees Celsius, pressure drop on the anode side and the cathode side as -0.2. High heating value efficiency 0.8 and similarly the voltage efficiency as 0.8. No Faraday efficiency was provided, so leave it as 1. Besides these specifications, you have two options to operate the module. One is for the provided power, calculate how much water consumption will be there or the makeup water is required for the given power. Or if you are not interested in calculating the makeup water, rather interested in calculating the power for the given electrolysis of the feed stream, then the model will calculate the power based on complete conversion of the inlet water. Let's proceed with the calculation of the makeup water. Additionally, you can define the cathode product flow or the anode product flow along with the expected product composition, or you can define completely the product composition on the anode side and the cathode side and calculate the product flow based on the makeup water and power consumption. In the example, it was specified that the purity of the cathode and the anode was 96%. So let's define hydrogen 96% in the cathode side and 0 oxygen leaving from the cathode side. Similarly, 0 hydrogen leaving in the cathode side but 96% oxygen in the anode side. The remaining 4% will be water entrainments in both of the product streams. With this, all the specifications are done. Let's save the file and run the simulation. Results are available. Again, to remind, just in case you have defined electrolyte NRTL RK model, then you will experience that the vapor fraction of the product stream is not rightly calculated. So you need to get back to electrolyte NRTL method. Also, if you have used two component approach while defining the electrolyte solution chemistry using electrolyte wizard, then the rigorous stack will not be able to simulate the problem. Then you have to get back to the apparent component approach. So let's have a look on the results. All the results related to the module are provided. In this case, the purity of hydrogen and oxygen in the product stream is defined as 96%. For this case, the heat duty calculated, energy consumption as well as water consumption are also provided. Stack current, stack voltage and cell current and cell voltage along with the powers are also calculated. Let's have a look on the stream results. Temperature, pressure and vapor fraction of all the streams. So you can clearly notice that there is no liquid passing the electrolyzer module. So that means all the liquid has been retained within the module or internally recycled to the inlet port after passing through the flash. Let's have a look on the mole flows. Here you can notice that besides hydrogen and oxygen in the cathode and anode channels, the remaining 4% purity is met by the water entrainments, whereas no potassium hydroxide has been considered or calculated or used in the simulation. Although potassium hydroxide was defined in the feed streams, but the module did not take into consideration for the simulation. So impact of having, besides you can consider that the flow rate of the inlet stream has also been altered from the specifications. Since in this case we have defined that for 20 megawatt power calculate the makeup water. So the makeup water for this case will be 215.2 kilomoles per hour to produce 210.98 cathode and 105.49 anode product streams with 96% purity of each product gas. The additional water and potassium hydroxide are neither calculated nor defined in the stream summary results. So that means virtually this module can be used for the simulation of other types of the electrolyzers other than alkaline electrolysis. Considering that the geometrical and electrical parameters though not defined in case of module but fairly corresponds to the alkaline electrolyzer. One very important parameter for comparison is the heat duty in both cases. Heat duty in case of module is almost 3.8 megawatt. That is the thermal energy that should be removed from the stack in order to operate it at 75 degrees Celsius isothermal conditions. But in case of rigorous stack simulation, the heat duty was calculated as 1000 kilowatt or almost 1 megawatt, and that is the thermal energy required to keep the electrolyzer at 75 degrees Celsius. And that is mainly because of the difference between feed temperature and the electrolyzer temperature. Feed temperature was 72 degrees Celsius and the electrolyzer is operating at 75 degrees Celsius. So to raise 3 degrees Celsius temperature, the electrolyzer requires almost 1 megawatt thermal energy in addition to the heat produced within the electrolyzer because of the electrochemical reactions. So this is how you can define the specifications of stack shortcut model, stack rigorous model and the module, and view the results of these three blocks along with the stream results. In this video, we have learned how to simulate batch reactor and electrolyzer available in the reactors palette. In the next video, we will talk about heat exchangers available in the exchangers palette. The heat exchanger blocks include a simple heater that can be used as a heater or a cooler, a co-current or a counter current heat exchanger block that can be used for the shortcut as well as rigorous simulation, including rating or design of the heat exchanger. Another block in the heat exchanger palette is the multi-stream heat exchanger and a different block that is HX flux. A different initiative that I have started is the preparation of self-assessments. The link for the self-assessment of each of the video is available in the description. I highly encourage to go through the self-assessment, solve the given problem and answer the corresponding questions to gauge your Aspen Plus skills.